Okay, remember with everything to do with E&M, all of this was developed in the 17 and 1800s, and they were literally thinking in terms of fluid dynamics. They literally thought the electric field was some kind of fluid that flows through space. So a lot of our terminology is terminology from fluid dynamics. So think if I've got a charge inside a box here, and the electric field, they thought of it as some fluid flowing out, passing through the surface of the box. And so one thing they might want to calculate is how much fluid flows through each, say, each pane or total through the box. Well, we call that flux. That's a term from fluid dynamics. Flux is the amount of your vector that passes perpendicularly through a surface times the area of that surface. Okay, so we've got a bunch of pictures here. We call it positive flux when something is flowing out from a closed surface. Negative flux if something is flowing in. So if we have a closed orientable surface, like a box here, with a positive charge, we would say we have positive flux flowing out. Remember, think of positive charges like you turned your sink on and water is flowing out into the universe. You build a box around that, water is going to flow outward through your box. We call that positive charge. Negative charges are like sinks. They're like holes in the universe where electric field is disappearing. It's flowing out of the universe. So if you've got a whole bunch of water around and you poke a hole in the universe, then that stuff will flow out of the universe into your box. We call this negative flux. Okay, well, what if none of my charge is inside the box? I just have charge back here and then I've got an empty box. Well, then everything that flows in back here is also going to flow out. Then that would be no net flux through the box. That's going to motivate Gauss's law later. Gauss's law tells us that the flux through a surface is the charge enclosed over epsilon naught. Okay, so flux. I'm going to build this up to the most general case. So we have our basic, easiest case. This is electric flux. So if we have a constant E perpendicular to a surface, say a square of area A, so I have some constant electric field here. I have this pass perpendicularly straight through a surface. So if this were my surface, my electric field might be coming straight out at us like this. Remember this convention with vectors. If you're drawing a vector on a flat surface, this symbol means the vector is coming out at you. Think of a vector like an arrow. That dot, you're looking at the point, the tip of an arrow. So this would be flowing up. And for completeness, if we were to draw this, these would be vectors flowing down. Think of it again like an arrow. You're looking at the back of an arrow. You're seeing the little feathers on the back of the arrow. Up, down. So I've got some surface here. Maybe it's sitting like this. Trying to find a piece of paper. I've got some surface and my electric field is flowing perfectly perpendicularly through it. Then the flux, Greek letter phi, will be the magnitude of E times the area. So our units then, we can see, will be E is newtons per meter, or newtons per coulomb, I don't know where I got meter from, times square meters. That's our most basic case. That doesn't happen very often. What if we tilt our surface? So still constant E. Now I've got E flowing. This is why I like to use the PowerPoint pictures, because I'm a terrible artist. I've got E flowing like this, and that's forming some angle with my surface. Then the flux through that surface will be magnitude of E times the area times the cosine. Now we got to be careful here. The cosine of the angle between E and the normal vector. This little angle phi here is between the vector E and the vector perpendicular to A. This is my angle phi, not this angle here. It's really easy to get this angle backwards, so homework questions try to test you on this. I can almost promise you, any homework problem or test problem where you're using this formula, they're going to give you the wrong angle on purpose. They're going to tell you this angle, you want this angle. So an example of this might be, I have a patch of earth here. Maybe it's 5 meters by 7 meters. I have an electric field, say in magnitude, E is 15 newtons per coulomb. So that's the ground, and E is pointing up at some angle here, 20 degrees. So like it's like this, like I'm flat on a surface, this is a 20-degree angle. Flux measures how much field flows through a surface perpendicularly through the surface. It's the perpendicular component. So what we're actually doing is we're breaking E up into its components here. I'm finding this parallel component and this perpendicular component. I want to measure how much E is flowing straight through the surface, not running parallel with the surface. Across from the 20 degrees here is the one I'm looking for. That would be sine of this angle, because that's not the right angle. I want to measure this angle. That's my normal vector. That's perpendicular to the surface. E is over here. This was a 20-degree angle here. The angle I want is this 70-degree angle. And we could see here, if we draw out our triangle, cosine of 70 would give us this component of E right there, the perpendicular component. So the flux through that surface would be magnitude of E times my area, which would be what, 35, times the cosine of 70, whatever. And then we just plug all that in the calculator. Make sure you're in degree mode. This would be in newtons per coulomb times meter squared. So if you have a problem that looks like this, I almost can guarantee they're going to tell you the angle between E and parallel to the surface, just to try to trick you. Flux is flowing through a surface. If I have some surface here and E is running parallel to it, there's no flux, because I'm not passing perpendicularly through the surface. In this case, the flux would be 0. newtons per coulomb meter squared. Don't forget units. Okay, we could take that up a level. This is our most general case. What if we have a non-constant E? So I've got some E field here. So maybe it's pointing in all different directions, different magnitudes. Think of it like a current flowing through a river or something. And then in there, I put some surface. So this is meant to be a 2D surface. Again, my drawing skills are not very good. So that's some, where's my piece of paper? That's maybe some bent up curved surface. Then the most general form is the flux through that surface is the surface integral. So this is a double integral of E dot ds, where ds is vectors perpendicular to the surface. So I draw in at every single point along this entire surface. I find a little normal vector. I take the dot product of that normal vector with E at that point. So here's my normal vector. Maybe at that point, E pointed that way. I take the dot product of those two. That gives me a scalar. This is a scalar integral. And then I add up all of those contributions all over the surface. It's a double integral. It's a surface integral. Okay, those are hard.